Buddy, for toughing the snow out there. I appreciate it. So I feel like I'm preaching to the choir here, but I'll say it anyway. It's no surprise that there's been a lot of evidence that we can generate a lot of knowledge from social media. I've listed some of my favorite examples here, including roadkill, as the sorts of things you can track by following online media. And today I'm going to briefly talk about some of my work in this tracking efforts, including the older work Mark had mentioned with influenza, alcohol use, and chronic illness. But moving forward, so all these sorts of information can be thought of as descriptive knowledge, right? I want to know, what is the state of the world right now? Can I infer it by monitoring what people are saying online, right? Is kind of how you summarize this. A more ambitious and dangerous task is to try to actually get to correlation or causal knowledge out of such data. So can I figure out, for example, what is the relationship between exercise and mood, anxiety, health, or drinking and hostility? So inferring these sorts of things is extremely difficult, as you know, even in any observational study where you have actual observations of the variables you're trying to measure. Whereas here, all we have is very noisy observations, in that we have to infer all the things we care about from text and social connections. Okay? So that's kind of where we're headed going forward. And today I'm going to talk about just some initial steps in this direction, specifically a trial looking at the relationship between exercise and mood, where these variables are inferred from social media. And as we'll see when we talk about this, I kind of view this as a test case to show what are the pitfalls of this method, right? So what are the dangers that happen if you try to do this? And the first obvious one that comes up is confounding variable bias, right? So what are all these other possible socioeconomic variables that could influence these things that we're trying to learn the relationships between? So the very first step in order to be able to control for those things is we have to measure them. They're not given to us. And so that's led to this whole other branch where now we have to go and infer all these socioeconomic variables based on the content online. So that was the motivation for the third part of the talk. So again, to summarize, I'll briefly talk about this nowcasting business, then this trial observational study, and then some of our more recent work trying to predict socioeconomic status from social media content. So when we first started this kind of health and social media thing, the first thing we thought of was trying to track flu rates using Twitter. And this fits into this kind of architecture has been used, I think, in a number of different domains, where the steps include things like, okay, here's all of Twitter or all of Facebook or all of whatever. I need to sample some documents, for example, all tweets ended in this particular week. I then need to classify them to say, well, how many of them are flu-related or expressing flu-like symptoms? I then need to count those up, aggregate them, and that gives me a number. This is my Twitter flu rate. But that's almost useless unless I know how it maps to the real world, which is where this validation bit comes in. So if I can then fit a model to historical CDC data, I can learn what is the relationship between my Twitter variable and the variable I actually care about, and then I use that for prediction going forward. Okay. So then when we first did this years ago, we started with this embarrassingly simple approach, which was our classifier is simply keyword matching. In this example, what we've done is we've just said, okay, give me all tweets in a given week, or some sample of them. Find the ones that match this set of keywords, and then fit a regression model that has exactly two coefficients, an intercept, and one mapping from historical Twitter variables to CDC variables. Okay. Then we can predict each week what the flu rate is. And we were surprised that this actually worked fairly well, both predicting on the tail end of the flu season as well as on the beginning part of the flu season. So we try to test the robustness of this by trying different keywords. And of course, it doesn't always work. And so for words like fever, for example, you might think is a good word to track. But of course, it's not a good word to track because of Justin Bieber. So that motivated, of course, our next step would be, well, let's just build a classifier and find ways to filter out the messages that really are about flu-related symptoms versus ones that aren't. And so in that older work, we developed some methods to do that, and you can reduce the amount of these kind of false positives. Right? So that was fun, and we said, well, what are the other things we can predict with social media. And so another thing we looked at was alcohol sales. Basically, the two criteria we were looking for was something that is measurable in the real world and something that people talk about online. So the measurable bit comes from the census, who tracks monthly alcohol sales volume by surveying industry. And then to track people online, we just, again, started with our simple keyword approach and said, well, what words should we track to determine how much people are consuming alcohol? So you can think about what words these might be. We picked a couple. I'll show you the first one, which was drunk. And so this is now at a month level. It almost worked, but didn't quite. So actually there was a shift around months 4 and 5 where the general trend seems right, but we're off. We're kind of lagging the actual sales volume, right? So it turned out we were off by a week, and that week was New Year's, right? So January 1st, 2nd, 3rd, we got a lot of tweets containing the word drunk, as in historically, what did I do? But the lag from selling the alcohol to consuming the alcohol to talking about the alcohol was quite a bit. So after a 7-day lag, that tended to track it fairly well. So this is, again, kind of a fun thing. OK, so this does another piece of evidence that there is some relationship between what people are saying and what people are doing, which shouldn't be too surprising. But I think there's now a wealth of evidence in a number of different domains, work done here and elsewhere, that have shown that there really is a pretty strong signal in this data source. So that work was all about looking at things over time. We can also look at things over space, right? So how do health outcomes vary by place, for example? Okay. So this was some work we did last year, estimating the health of a county based on the language that they use online. Right. So we kind of took very much a data mining approach to this, which was give us as many variables as you can about a county, and we'll try to predict them. So there's a great project called the County Health Rankings and Roadmap Project, which essentially aggregates all these different government surveys that they're taking annually or less, which tie health-related statistics to the county level. Okay. So for every county, we have values for all of these variables. And you can typically try to estimate these things based on the demographics of that place, right, or socioeconomic values of that place. And so we were asking was, does the Twitter activity of a location provide any more information than the demographics of that location at predicting these values? So what we did was we took the 100 most populous counties in the US, and we collected a number of tweets from each county. And then for each county, we created a giant feature vector, which in this case only contained 160 variables, which were, so we used several different lexicons. So the Luke scores, many of you are probably familiar with. PERMA is another lexicon out of Penn. And we separated those into, for each token we see, does it fall into one or more of those categories? And furthermore, we distinguish between those that occurred in the actual tweet itself versus those that occurred in the description, the profile description of who I am. And then we create a vector that says, OK, 12% of all users in LA County mentioned a word from the affect category in their tweets. Okay? So now we have another representation of each county, which we can use to try to see which of these things correlate with health outcomes. So we literally fit 27 different ridge regression models. So for each one of these things, I now have a beta. So I have a beta that says how related is D equals self for obesity, same for do you have health insurance, et cetera. So we want to do two things. We want to see what is the predictive accuracy, and then what are the highly weighted coefficients here. So if we just look at raw correlation, we can see that, so this was held out, I should say. So for example, you'd do cross-validation and fit on a subset of the counties and predict on the remainder. You can see what is the correlation between our predicted health outcomes and those actually reported by the census data. And we see across a broad range of metrics, there's somewhere between mild and strong correlation held out here. It's actually a little tricky to try to compute statistical significance if you care about that kind of thing. So we have to deal with spatial autocorrelation here, which is why the highest magnitude correlations are not necessarily the ones that are most significant, that are actually significant. So then we say, well, compared to what? So we next took a model that was predict with 4 variables of age, gender, race, and income of a county. and did the same thing to try to predict those 27 health outcomes. And then we just wanted to see, well, what was the delta? So how much did we improve by including Twitter variables to these 4 demographic variables? And so what we found, again, across many of these, a little over half, we were able to actually add value to our, here I'm reporting, this is a variant of mean average error, mean absolute error that's normalized by the range of the outcome variables so that we can compare across outcome variables. So the point here is that adding these Twitter variables can improve your prediction accuracy across the wide range of these tasks. We can then look at, okay, what are the actual coefficients being placed on each of these linguistic variables? And then does that tell us anything about what this model is actually learning here? Again, we have to be a little careful to deal with spatial autocorrelation. So we use spatial two-stage least square, which as essentially a lag variable for geography. And use that to determine which of these coefficients were significant predictors of these health outcomes. So I'll just show a few of these here. There's one in the paper. So socio-emotional support. So there's literally a survey that asks you, think about your social support structure. Do you think it's good, bad, kind of okay, right? Think about your friends and family, that kind of thing. So places where citizens report higher social emotional support tend to have higher religious references in their Twitter accounts, references to others, as well as positive feelings. So there's the positive emotion category here. Places with less, people who report less social emotional support tend to have more words talking about TV and movies, et cetera. Yes?
On the previous slide, yeah, so just the chart, actually.
The chart, yep.
So was this just one additional variable in addition to the 4 demographics?
No, this is 160. So it's a 4 variable model versus a 164 variable model.
So what is the, okay, so I'm trying to figure out what the different numbers are for the different.
So this is the percent improvement. So if you pick the model that just uses 4, and you get an error rate.
Right.
And you do the model that has 164, you get the error rate. And you look at the relative change.
Oh, are these different categories of?
These are different Ys, yeah, different output variables.
Oh, okay.
Yeah, sorry. Yeah, so these are not the linguistic variables. These are the outputs that we're predicting.
Right, okay.
Yeah, sorry. Right. So 27 different regression problems.
And one basic thing that
Yeah.
you figured out in your regression formula
Yeah.
is that you have your ground truth, and which is provided by somebody, CDC, sensors, whoever.
Right.
And they have a spatio-temporal sampling density, if you will. You might have it at city level, county level, whatever.
Right.
And they will be monthly. And then you have your observations, which are your tweets, and they have a spatio-temporal density. How do the two match up? Because after all, you're trying to make a prediction on one of them from the other, but your sampling could be very, very different.
Exactly right. And we expect the sampling to be extremely different, not only in terms of density, in terms of demographics and other things. That's right.
That's what I'm saying. So how do you connect?
Exactly right. So we actually, I hid those slides, but I do have slides on that. So yes, for example, let's just say that we know that we have many more young users in our sample than the county has in their sample, the census has in their sample, right? So my first answer is, well, it matters, but not that much, as long as there's a strong correlation between the health the term. So what we're saying is that counties where young people use these terms correlates with counties with high social support, right? Suppose the only people on Twitter were those people under age 25. You know, there would still be a signal there in terms of prediction.
But I'm worried about more things like the alcohol data. Like, if I look at Baltimore City, there are these clear social, anthropological, whatever studies which show you where all the liquor stores are concentrated in the poorest areas of the city, where people can't even afford to eat well.
Right.
Below 3. And your sales data probably is coming from everywhere, and tweets are coming from, let's say, Roland Park or the affluent parts of the city. And then, sure, there may be a correlation, but I'm not sure whether it's just chance or whether there's a way to normalize it. Yeah, that's right.
So so that's a great point that is prevalent in all of this work, right? Is that there's this bias in the data we're getting. So for this work in particular, we did another study where we tried to predict the demographics of our Twitter users. So say we're able to predict, for example, the ethnicity and income of a user. We can then do standard survey weighting techniques, right, to kind of overweight the ones we have not enough of in our sample. And that can improve your predictive accuracy in those cases, yes. But that's, so the third part of this talk is all about demographic prediction. And that's one of the core reasons why I think it's so important, is exactly because of that mismatch. Yeah, and I apologize, I'm kind of flying through this work at a very high level of detail, because it's more than a year old, so I'm trying to get to the newer stuff. But I'm happy to talk more about this stuff offline. Okay, so that was, that whole part one there is just all about finding evidence that the stuff people say online correlates to the real world. And again, I think the evidence is mounting that that's true, even despite of that sampling bias, right? A lot of these studies don't control for the sampling bias, but still have a lot of predictive power, I think because there's a correlation between the sample we do have and the whole population. So the next phase I see in this kind of branch is, okay, can we go beyond just tracking things to actually trying to figure out the relationship between things? So this is what I've been calling web-scale observational studies. And if you think of a traditional observational study, like in epidemiology or other social sciences, for example, you essentially have your response variables and your explanatory variables, right? And you want to have a pool of, hopefully representative pool, where you've annotated those two variables, and then you can look for the differences. Like, okay, how much more likely is my explanatory variable given this particular response variable? Right? So does smoking cause cancer would be the kind of canonical one. So generalizing that to social media setting, right, where we have to actually sample some users, some people who will be in this observational study, we then need to, we're not giving, in typical cases, we're not given the assignments to these variables, so we have to predict them somehow. And then with these predicted, we can then label all of our users and then do standard hypothesis testing on top of that to figure out, is there a significant difference between these groups? Okay. Now, as you can imagine, this is plagued with difficulties. Again, we have to infer all these variables. There's going to be uncertainty over these variables, and so we have to also propagate that uncertainty all the way to the end of hypothesis testing. Right? So that's kind of where we're trying to get to. And to start in this direction, we chose a particular application where we're looking at the relationship between exercise and mood. We wanted to, our goal here was to investigate how the particular design choices you make and the particular confounders you consider or don't influence your results. I'm very worried about stepping in this direction and coming up with erroneous conclusions, so we have to be careful about how we do these things. So our question is, okay, if you exercise a lot, does that affect your mood? Right? And there's actually been a lot of health studies on this that are actually somewhat mixed. That it may help reduce anxiety in certain cases. It may be a short-term effect as opposed to a long-term effect. So there's some uncertainty on this, but there is some a lot of interest in how these two things are related. So we have to label these two variables to collect people for our study. For the exercise one, we actually just take a very simple approach, which is there are these fitness applications, right, where you track how much you run, for example. So you can hook these up to your Twitter account so that it'll tweet, and it'll say, Aron just ran 5.2 miles today in whatever, 45 minutes. And it'll tweet that out. And so there's a collection of maybe 9 or so of these hashtags that we can use to very quickly collect lots and lots of users who we know, based on this history, are very active. Right? If they're running 5 miles a day, they're very active people. Okay? So, of course, when we say exercise, this is now a very specific type of exercise. Right? This is people who run a lot, and so that's our kind of variable here now. Mood is obviously trickier and grayer, so we're going to use a classifier for that one. In particular, we build on, past work has used this profile of mood states, which is a psychometric test. You take this survey, and it assigns you different categories along different dimensions of mood. And so the three dimensions we looked at, which we picked because the health literature suggested that these were the ones most likely to be affected by exercise, were dejection, anxiety, and anger. So these are 3 positive examples. So we labeled some data for this. These are some of the positive examples. This was the least offensive anger tweet I could find to show you. So we actually there's a lot of details here for how you collect these things, right? So what we actually did was started with the profile of mood states has a list of keywords that are associated with each of these moods. We then expanded that set of keywords by doing essentially synonym extraction from Twitter, right? So find all the context these words appear on Twitter, find the similar words. And now we have maybe 100 keywords that we think are somewhat related to these things, right? Then we use those keywords to collect the original tweets that we then label. So essentially all this pre-processing is to find things that are at least somewhat likely to be related to these different moods and then label those ourselves. Okay. So we fit this classifier and it does okay, not wonderful. Important to remember this is again just those tweets that contain some of those 100 keywords. So this is really how well can we distinguish between like polysemous uses of terms like sad or something like that. Okay. And it's maybe not too surprising that hostility tends to be a little bit easier to predict than the others. So our response variable now is what proportion of a user's tweets were classified as exhibiting either dejection or anxiety or anger. Right? So that's our outcome there. Okay, so currently so far all I have is people who run a lot and their mood, right? As predicted by this classifier. I need somebody to compare it to. Right? So this is the whole problem of selecting a control group. So the first thing we try, which is as much as anything is common, is somewhat common in this kind of work, which is, well, let's just pick a uniform sample of users from Twitter and run the classifier on them. We get their mood states, and then we can compare to these people who exercise a lot. Of course, this ignores the giant confounding bias that demographics will influence both whether or not you run 5 miles a day and use Fitbits and whether or not you express certain moods online on Twitter. Right? So we want to deal with the demographic issues. So to do that, we use a matching approach. So for each user in our athletic sample, we wanted to find another virtual twin. Okay? And we did that by looking for another user who was a friend of the athletic user by looking at symmetric follow relationships. So I follow you and you follow me. In the same, ideally the same city. If we're not able to find that, we back off to the same state. And then the same gender. So both location and gender we got from the profile. So just using the first name and census data to figure out your gender. And then city state also based on the profile with some normalization on those strings as well. Okay. And then we also wanted to kind of normalize for the type of Twitter user you were. This is a little bit different from other work which actually wants to look if these things are actually explanatory variables. Like maybe people who tweet a lot for some reason tend to be angry or whatever. But we wanted to control for those things, so we tried to find essentially the person who used Twitter most like you and met these other categories, okay, to try to reduce that. So now we have our athletic group and our twins, our match group, and now we're going to look at the difference in the classifier right there. Yeah.
So are we going to be able to tell the difference between whether the exercise helps the one friend feel better or whether it depresses their friend that they're
So the causal link is I exercise and you get depressed? Yeah, I have not controlled for that one now. Yeah, that's right. So not only are you exercising, you're broadcasting it to everyone. So this is kind of an interesting effect there. Okay, so then we looked at the results. So this is just reporting for each of these three mood categories, what is the percent reduction in that prevalence attributed to exercise? So comparing the random group to the ones that are athletic, this says that there's a 21% reduction in the frequency of hostile tweets, okay? And a 5% reduction in the frequency of dejection tweets, a 7% reduction in anxiety tweets, okay? That's kind of the initial result compared to a random baseline. And so we do this, we say, oh great, statistically significant, done, right? So then of course we compare to our match group, and two of the effects stay there, although at a smaller magnitude, and the third effect goes away completely and is slightly negative, although not significantly so. Okay. So to me, that's the main point of this bit of work. It's not so much that we can come up with these effect sizes and estimate them, but just how sensitive they are to how we control for things. And if you're a social scientist or an epidemiologist, this is 101, right? Obviously, you need to control for these things. But the problem is in our studies, we don't have these things typically, right? So in the study, we used heuristics to come up with the things with which you're controlling for. And it's a very small set. And I think my point going forward is we need to expand the set to a much wider array of variables to reduce this confounding bias in these types of studies. Okay. So why does this happen? So we just look at, for example, what are the characteristics of the random versus the matched group. And we can see that the matched group has half as many females. So it turns out that the people in our athletic group tended to be mostly male. And then also location varied a lot. I'm just showing California. Of course, it varies by state as well. But this is also showing that athletic users tend to be more from California than a random sample of Twitter users. I should say the random sample is restricted to US and English speaking. That's, the fact that these differences can be so large suggests that we really need to control for them when we're trying to make these kinds of conclusions. Okay, that was our first foray into trying to do an observational study from social media and kind of looking at all the difficulties that it brings up. So the main difficulty, as I've said many times now, is we need to predict these confounding variables, right? So our web-scale observational studies need this demographic or socioeconomic status information. And this is true for all the things I've talked about so far, both for controlling for confounding bias, for controlling for sampling bias in the earlier studies, as well as just very simply stratifying, right? A lot of the health people I talk to, they just want to know, okay, take this demographic group and tell me, how do they compare to this other demographic group with respect to this type of message? And we can't really do that confidently yet because we're not able to predict these things. Okay? So that's what this last part is going to be about, is just how can we infer the demographics of Twitter users. So there's been a lot of work on this. Many folks here have worked on this problem. A lot of the kind of initial approaches relied on a lot of labeled data. So somebody sits down and says, here's 1,000 users. Here's the ethnicity, if you can judge it from maybe the picture or maybe what they say. Here's the, maybe you can guess their gender or possibly age, right? This is difficult for many reasons, one of which it's hard to label that data. What a lot of folks do, myself included in the past, is just look for certain phrases that reveal the label, right? So look for people saying, this is a clever one that I did not come up with, which was look for people saying, happy 22nd birthday to me, right? So now you know their age. And similarly, you can do similar things for other types of categories. Of course, that introduces a lot of bias because now you're just restricting your label data to people who actually explicitly say what their category is. The other problem, of course, is that humans may not be able to label all these things. So it's kind of difficult to look at a user profile and put you in an income bracket, for example. You can guess, and maybe those guesses are okay in aggregate, but it's pretty hard to do at an individual level. The other thing, of course, to do, which is great if you can do it, is to get survey data. So here's, for example, 600,000 Facebook users and the output of a survey they took. Right? So this is a study that's been done by Schwartz and a couple others. So that's great if you can get it. Even that, though, is tough to update over time. I think this is the next slide. Yeah. So especially on social media, we were talking about this earlier, right? A classifier we build today could be outrageously bad tomorrow, right? So think about it, especially these linear classifiers, right? There's some coefficient tied to some word or phrase or n-gram. And all of a sudden, that n-gram blows up for some reason. And everybody's using this n-gram, like beaver fever earlier on, right? So this data drift I think, is a huge problem in all of this work. And to deal with data drift, we really need methods that don't rely so much on static labeled data, right? We need this model to be updated literally every day in order to trust its predictions over time. So that's some of the limits of supervised classification, why we're trying to find ways to do this without having to label individual users. So this was kind of push us in the direction of sometimes called lightly or weakly supervised classification, where your labels don't come at the instance level, instead they come at the aggregate level over a bag of instances. Okay. So can we learn models from aggregate data and apply them at the user level? And there's been actually some work here and elsewhere that attempted to do this by, for example, if I know the distribution of last names by ethnicity, can I inject that as a prior to kind of learn models that way? So I'm going to talk about one and a half approaches. The first one is going to use supervision from web traffic demographics, which I'll explain what that means in a second. And this first approach is using purely the graph. It's not looking at text at all. Just looking at, for example, whom you follow to figure out your demographics. So Quantcast is a so-called audience measurement company, and their job is for every company's URL, they want to be able to output some statistics about the visitors to that URL. Okay? So first of all, just the number is very important, but also their breakdown demographically. They do this, in a proprietary way, but part of the sauce involves a lot of cookies going around, and also a web panel. So there's a set of people who have a browser plugin and have also completed a survey that tells the company about their demographics, and then they can see which sites they visit and how often. So you can get weekly or monthly statistics about who's visiting which site. So in this study, we looked at 6 different variables, so ethnicity, gender, age, education, income, and whether or not you have children. And we wanted to predict those based on Twitter. So first of all, of course, we have to make the leap that I have lifehacker.com's breakdown of demographics. I'm now going to tie that to @lifehacker on Twitter. Right? So the core assumption of this work is that that's a reasonable mapping, right? That the people who follow Lifehacker on Twitter are at least somewhat like the people who who visit lifehacker.com. It's actually not quite that strong. We just care that the relative differences are the same, right? So if there's twice as many females visiting lifehacker.com, there's twice as many female followers on @lifehacker. So what we do is we take lifehacker.com, we then find the Twitter account associated with that. We look at the social graph, which I'll talk more about on the next slide, featureize that thing, and then use it in a regression model where here I'm predicting, in this case, 6 different, well, actually more than 6, because for each one of these I'm going to have a different regression model to predict the percentage of followers of @lifehacker that are Caucasian, for example. Okay, so regression models for all these things. So what does that feature vector look like? It's quite simple. So for Lifehacker, we create what we're calling the neighbor vector. So Lifehacker has 2 followers, A and B. And A follows C, and B follows C and D. Okay. So I don't really care about A and B as features in my model because nobody follows A and B. They're just like normal folks like me and you, or like me. But what I do care about is C and D because those are related accounts to Lifehacker. And they're going to be more popular accounts. They're going to have more followers. So our vector is very simply the proportion of followers of Lifehacker that also follow C, which in this case is 100%. The proportion of followers of Lifehacker that also follow D, which in this case is 50%. Okay, so this very simple measure tells me that account C is more indicative of the followers of Lifehacker than account D is. So in this experiment, we have about 1,000 of these brand level accounts. We sample a very small number of followers of each of those accounts. In this case, 120 followers for each of these accounts. The reason that's so small is because then we have to turn around and find all the people that they follow. Right? So 120 times 1,000, we have to do that many calls to the Twitter API to get the friends of A and B. Okay? So we get 5,000 friends per API request, which gives us is how we can create this neighborhood vector, which at the end of the day, we end up with 1.6 million unique neighbors. So these are the C's and D's. But then we filter those to those that occur at least 10 times. We want those that are at least somewhat popular. Okay? And that gets us down to around 40,000. So now we have a feature vector of length 40,000, one for each of these Twitter accounts in the neighbor vector. Does that make sense? Okay. So the first set of experiments is just looking at, well, what is our held out correlation with Quantcast? So this is just an aggregate prediction thing. So we're going to essentially ask, can we predict the percent of Caucasian people who visited lifehacker.com today based on who their followers are on Twitter? Okay. So the first thing we did was use ridge regression here, so L2 regularizer on the coefficients. What actually ended up helping were 2 things. One was so-called elastic net, which essentially just combines the L2 regularizer with an L1 regularizer to encourage sparsity, right? So we small number of non-zero coefficients, as well as restrict their magnitude with the L2 regularizer. The multitask bit just has to do with the fact that, well, if I'm predicting age brackets, these are clearly not independent things. So I don't necessarily want to have completely independent models to predict those things. So this multitask bit is kind of a way to get at that. And all it does is say that the L1 regularizer, sorry, I have giant graphics that take 6 seconds to load. There we go. The L1 regularizer should pick the same coefficients that are non-zero across each of those subtasks. So say for the age problem, say 6,000 of the coefficients are determined to be non-zero. It's the same 6,000 coefficients for the first age bracket, the second age bracket, the third age bracket, okay? So that ties them a little bit in the fact that they at least are restricted to the same features. Okay, so we run this across all the different demographic attributes. And we get very strong correlation across them all, 0.77 held out again on average. Here I'm just showing the best and the worst. so each one of these dots, remember, is a brand. X-axis is what the Quantcast reports for their demographic breakdown. The Y-axis is what we predict based on their followers. Okay? So gender tends to be a little bit easier than age. Again, as you can imagine, there's a sampling bias effect here. Right? We can also then just look at the regression model and look at the top weighted coefficients. So these are literally the top 5 coefficients in the model for each of these categories, and they're sometimes depressingly stereotypical. So this says that guys like sports, that women tend to like these particular TV personalities, that young people play video games, that older folks like the news and the White House, that college people like comedians, that grad students like elitist publications, and that's all of them. So I feel like our feature representation was pretty simple here, right? We're just looking at essentially 2 hops away, but I think the power comes from aggregating them across all these followers, and even this this kind of weak source of supervision, right? It's one step removed, visitors to a website versus Twitter followers. The accounts that come out highly weighted are pretty convincing to me that something's going on here, right? So the next step, of course, is, well, can we take this and now apply it to actual individual users rather than predicting a group of users? I should say predicting a group of users is actually very useful. We need to do more experiments to determine, well, okay, I took a group of users determined by those who follow brand X, but there are many other ways I could have picked a group of users, right? Find all users who use this term, right? And predict their demographics using the exact same feature representation. So it's not quite clear that we can do that. I mean, we can run it and see what happens, right? But there might be something about the way that these guys are grouped together that allows us to work better. But in this case, we're just going to look at individual users. And we do something very simple. So here's a particular user. We know that this user follows these 3 accounts. Can we predict whether or not they're male or female, right? So we do something very simple. We literally take those betas that we learned in those regression models, standardize them, so they're comparable across output variables. And then we literally just predict the label with the highest dot products, right? So take this guy, we'll get this I believe guy, will get a feature vector where there's 1 for ESPN, 1 for Wired, 1 for Wall Street Journal, and 0 for everybody else. Take the dot product with my betas from before, and just do that for male and female and pick the highest. We compare this with a supervised learning approach using logistic regression. So we did finally settle down and label some data for ethnicity and gender for validation purposes. We also use this to fit the regression model, the classifier, the supervised model, just so we can compare with the supervised approach. So results here on the top is for gender. So the dotted line, of course, the x-axis is as we add more training data. So the idea here is, okay, if I could spend another $10 labeling data, how much will my accuracy go up? And so the x-axis is what % of the labeled data I'm using. The y-axis is macro-F1 across the different classes in these categories. So gender is looking good for us, right? So even after giving the classifier all the training data we can, right? We're doing cross-validation, of course. the regression approach still does slightly better on this particular data set. Ethnicity is a bit more mixed. It looks like, after half the training data is used, you start to get better accuracy by using just a plain old supervised classifier. Right? Yes?
When you say you labeled data for this?
Yeah.
How do you label that?
Sure, yeah. So for this one, we, let's see, uniformly sampled people from the United States who used English. We sampled 1,000 of them, and then we manually label them for ethnicity and gender by looking at their profile and guessing. And then we did inter-annotated agreement to see how much our guesses correlate with each other.
In the previous experiment, you allowed for communication.
That's right. Well, in the previous experiment, for gender, we picked it just by looking at the first name.
That's because for gender, at least, that data is based on, you can train a gender classifier census data.
That's right. Yep. So you can just take census data, find all the people who actually post their first name, right, and take the most, and just train a classifier on that. That's correct. Yep. Yeah. So for some of these, like gender, is probably less. Unfortunately, it's the one we do better on, but it's probably less motivating for this particular work because it's kind of easy to label automatically. But these other ones are less so. Yeah.
So are these supervised classifiers trained on just their set of followers? So
That's right. The feature vectors are the
trying to
same.
compare the regression approach to this, and the features are the same.
That's exactly right. Yeah. So the features are exactly the same. So none of these approaches use text, which is why these results are lower than in some of our subsequent work that does use text, and some other work here that does use text. Right. This is just using link information. Right. The other thing we looked at was, well, what if I hide some of the friends of a user? So like how many non-zero feature values do I need from you in order to make a prediction? This is basically showing that it plateaus very quickly in this domain so that even after knowing, if I know 10 of the people you follow, these were chosen uniformly at random from the people you do follow, I pretty much start to plateau at accuracy here. So. This is good for us and bad for privacy, right? Because if I know just a few of the people you follow, that can tell me a lot potentially about your demographics. Okay, so that work was just using, I'm pretty much out of time. That work was just using the social network information. We have a paper coming up very soon that extends this in a couple of ways. First of all, we add text features. Second of all, we add different sources of this aggregate information, right? So we have census data at the county level that tells us stuff about ethnicity, that tells us stuff about age, that tells us stuff about gender. We also have name demographics that's been used in some other work that says, for example, the median age of somebody named Brittany is 23. And we can tell this from other census data. Similar things with last names and ethnicity. There's similar constraints there. So now we got all these different constraints that are giving us some aggregate information about what we expect to see in this bag of instances. And we use a different approach here. Rather than using just plain old regression, we use label regularization, which, here's the approach here. So for example, say I have 1,000 tweets from this county, okay? And I know from the census that this county is 70% white. Okay? So that's what my p tilde will tell me. P tilde is what I expect the label proportion to be in this bag. And then p hat is what my model predicts. Okay? And so I want to train my model to minimize the cross entropy between these two things. So I want my predicted label proportion to match the census proportion as best as possible. Okay? And the nice thing about this, so this has been used in the past for different applications. What's a little bit different about how we're using it is, first of all, we don't have a labeled part of this objective function. It's only an unlabeled portion, right? Only aggregate data. Second of all, we're actually adding in a whole bunch of these constraints, right? So there's a bunch of these sums for each one of those constraints, which may be over different sets. So U of J here would be like one of those counties for which I have that. U of K could be the people for which I have first names, right? So these are multiple different sets that could be overlapping, and they're going to have constraints that are competing with each other on these things. First of all, so yes, there's overlapping and competing constraints. Second of all, these constraints are all very noisy. Again, so this census data tells me that half of this population is above 30, but age is going to be very distorted on Twitter there, right? So in this paper, we took a pretty simple approach, which was to use forward selection. So think of it as feature selection almost, right? So I want to pick, so say I've got 1,000 constraints like this. Which subset should I use to fit my model in order to maximize accuracy? And so in this work we found we compare again with a standard supervised baseline here that uses text features as well, and find that for a few of the tasks we can do as well or better than supervised learning. So this is for ethnicity and political affiliation classification. We can do as well or better as supervised using no label data. But where it does poorly is exactly on age classification. And I think it's exactly because of this mismatch between what the constraint says and what the sample pool looks like from Twitter. And so that's what we're working on now as a way to explicitly model that mismatch in our classifier to adjust for that difference. So in summary, I've tried to give an overview of a few different branches of work we've been doing, both in the noun casting regime, in what I believe is kind of the next frontier in observational studies online, and then this third part, which is an outgrowth of that second part, which was we really need this socioeconomic variables to do these observational studies. And there's a lot of future work looking at, of course, improved demographic inference, dealing with these noise in this variable when we do these observational studies. So I have distributions over the output of my classifier. I should really be taking those into account. Doing some better validation, both comparing with surveys of Twitter users as well as look at the effect size determined by normal observational studies and using that as a way to kind of validate what the output of our system says. And then looking at longitudinal studies is also another way to look at the relationships, cause and effect relationships. So. All right, that's it for me. Thanks for your attention and for braving the snow again.
Any questions?
Yes, sir.
The graph that you had following my previous question,
Yep.
flickers off. So these friends were the Martha Stewart's Twitter friends, or they?
Right.
So these like the really heavy anchors. So then, what is the distribution over the number of friends that people that you're classifying actually have?
Yeah, good question. I have that in the paper. I don't have it off the top of my head, but so as you could guess, there's like a lot of people who follow a small number, and then there's a few number of people that follow a lot, right? So, I mean, part of the tapering effect could be that I'm just hitting, a lot for this particular labeled data set. Maybe half of them only have 50 users to begin with, right? But I don't know the exact distribution, but I have it plotted. Yeah. Yes.
So a general problem with all this stuff is you have this missing data problem.
Mm-hmm.
Or for example, your Fitbit example, it's safe to assume that if someone tweets that they exercised or they ran for 5 miles, that they ran for 5 miles.
Mm-hmm.
But if they don't tweet that, it's not really safe to assume that they never exercised or they just don't tweet about it.
That's right.
So I'm sure you've thought about this, but do you have any thoughts on how to deal with this in your work or in general?
Yeah, no, it is a tough problem. Of course, you can always build a classifier, right, to try to determine that based on the way they tweet. But that's a problem with all of this work, right? So the lack of saying something, does that mean that it's not true, right? I think ultimately you want to have a latent variable for that fact. And you're going to have to integrate over it when you're drawing your causal inferences, right? There's no easy way around that I know of.
In defense of your result,
Yeah.
I don't think you use anywhere the fact that, or anywhere a statistic about how often, for example, these other users were angry or whatever that particular sentiment was. You're simply looking at mood versus whether or not you exercise on a random sample versus mood and whether or not you exercise on a matched sample. So you never really asserted that it was any different from the normal population.
Oh, I should, I'm not sure if this answers your question, but these graphs were saying, what's the difference between the match sample and the athletic sample? I am looking at the proportion of tweets that were classified as anxious in the matched pool versus the exercise pool, and that's what this difference is.
Right.
Yeah.
In other words, the match pool is just assumed to be regular people.
That's right. And so I think the point was that, okay, some of those may actually exercise a lot.
Right.
So if anything, I'm just being overly conservative here, right? So, so the magnitude could be larger.
Yeah, that's what I'm saying.
Yeah.
You're not overstating your result, which is good.
Could be
but
understated.
We might actually find that there is something here that you weren't able to pick up.
That's exactly right. Yep. Mhm.
But yeah, that's certainly a better problem scientifically. Yeah.
Right. yeah, yeah, yeah. So, okay. Yes.
So back in the nowcasting section,
Sure.
You found really high correlations
Mhm.
between the data you were able to find on Twitter and what we already know about the population.
Right.
So I'm just wondering, is this just showing us that history is repeating itself, or that the CDC is doing its job right, or is there something that you're trying to get at that's new from this?
Yeah, good. So I mean, part of the motivation for this kind of work was more about cost and time, right? So if it takes 2.5 weeks and however many thousands of dollars to compute this number, then if we can have that 2 weeks in advance, that could be useful, right? So certainly for infectious diseases, that's kind of the motivating factor. So that's one part. But to me, the part is part of a validation thing, right? So if we believe that this thing is representative of the world, now can we start to use it for these observational studies? Right.
Just with the historical data that it matched up so well, then maybe it's just showing us that history is repeating itself.
Oh,
No, when you say historical, they're just going to conduct the study after they get the data for that time. So it's the same time.
Got it.
that's right. Yeah. And so we predict into the future. Yeah. So what this graph is just saying is like, okay, if I never see CDC data from week 20 on, what are my predictions? Right? So if CDC shut down on week 20, that's what that's saying. Okay. Anybody else?
All right,
All right.
let's thank Aron again.
Thanks, guys.